and we're in business.
Yep.
Right, Casper, we're going to start off very quickly going over the Wheatstone bridge because we need to see how that builds up to the Metre bridge.
So you told us you only need to perform it.
Yes.
Don't need to be able to derive it. And I found a question where they asked us to derive it.
That, if you found a question, it would have been on the sample papers.
Maybe.
Yeah, so it shouldn't have come up. It wouldn't come up. So what he's saying there is the derivation of this, which I am going to go through, you don't have to know for exam purposes. However, it's a very good revision of electricity anyway. So what we basically set it up like this, we have a power supply, 4 resistors, and the idea is we keep chopping and changing the resistors until what?
Until it goes meter, whatever is equal.
Okay, I've got a meter. Until what about the meter? What do I attach the meter to?
To the current.
Where about?
Oh, to
Not ANC.
B.
This guy up here, and that guy down there. So I put that there. So now I keep changing the resistors until what?
Until it's not deflecting.
Until this guy here isn't deflecting. So basically, current can go up and go down here and out, or it can go down up there and out, or it can go just along the top, or it can go just along the bottom. So what I do is by trial and error, and this is why it's unrealistic, because you can't keep popping in and out resistors. That's why it builds up to the meter bridge. But theoretically, if I kept popping resistors in and out until this guy here no longer deflected. It's a galvanometer, it deflects if current is passing in either direction. So if it's not deflecting either way, it means no current is passing from B to D. If no current is passing from B to D, what can I say about the potential difference between these 2 points?
Was it very low?
Go better than very low.
No.
0. If there is a potential difference between 2 points, any 2 points, if I've got potential difference between A
because
and B.
it's the work done in taking the current from one point to another.
Very good.
So if there's no current, then...
So if there's no current, then there's no work being done to bring current from one place to another. That's one way to think about it, which is perfect. Alternatively, if I say, what was I going to say there? If I put a little galvanometer here, if it's not moving, it means there's no current going from there to there, and therefore, as Jan said, if there's no current going, then there's no work being done to go from there to there, therefore the potential is 0. Another way of looking at it is we twist it around and say, what drives current? Potential difference is what drives current. It pushes the current around, right? So if there's no current, there must be no potential difference. Finally. If there was a potential difference, there would be current. Because now you might, in some cases, if you have a potential difference, you might get a very small current. In what circumstances? If I have a potential difference, so I am pushing, but I'm getting a very small current, that must be a very high resistance. But in this case, I know my galvanometer has a very small resistance. So if there is a potential difference between these 2 points, and there's no resistance, well then I have to get a current. Or conversely, if there's no current there, then there must be no potential difference between B and D. Okay? So the first thing I write down is the potential difference between BD, VBD equals 0. In fact, I probably should have that in the middle. Oh no, we'll just leave it there. VBD equals 0. If there's no potential difference between those 2 points, what can I conclude about that potential difference and that potential difference?
It's the same.
They're the same. You've got the same common point between there and there. You've got the same beginning point, sorry, and there's no potential difference between the 2 end points. So if there's no potential difference between the 2 end points and that point is the same, well then there must be no potential difference between there and there. So therefore you say VAB equals V what?
AD.
AD. Now I want to ultimately finish up with a formula that relates resistances, R1 over R2 equals R3 over R4. How do I bring in resistances in here?
The current and the current.
Instead of saying VAB, what can I say?
I1.
I1,
R.
R1. Yeah, in other words, the potential difference across there is equal to I multiplied by R. And it's just the I1 multiplied by the R1. So I1, R1 equals, what do we have down here?
I2, R3.
I2, R3. Now similarly, we can come over here and say if VBD equals 0, what does that tell me about that potential difference and that potential difference?
Equal.
They're equal. So VBC equals V what?
DC.
VDC, and now I want to write that in terms of I's and R's.
I2 R.
VBC, be careful.
I1 R2.
I1 R2 equals
I2 R4.
I2.
R4.
Why is Karina the only one talking here?
So
Electrical.
why? Oh no, hang on. So the current is the same everywhere for the top and the bottom line. Why is that? Oh, because okay.
Is I1 equal to I2?
No.
Very good, and that's the misconception that people have, and that's, I think, oh, I'll just give it, in case anyone else is watching and wonders why that not is the case. You often think that if no current is going from there to there, well then that current must be equal to that current. But it's not the case, and I make the analogy, you could have a big river going down in that direction, you could have a very small channel going down in that direction, and if you connect the two of them up, let's say they're a mile apart, and you put a little leaf, and I'm going to represent the leaf with the arrow. I can have a big current going down there, a big current going through here, but let's call this guy point B, and keep the same notation, this guy here, point D. Will current always flow from B to D? Sorry, I'll rephrase the question. Under what conditions will current not flow from B to D? Sorry, I should say water. Under what conditions will water not go from B to D?
If D has a higher potential, no, a higher resistance than B. If the flow of the current is quicker
Because
than
it's
B.
Okay, we're just talking back to water. We're just thinking about water. Big flow of water here, small flow of water here. I'm saying I can get a big river going down here and a small drain going in this direction. They'll all be full of water now. And I'm going to say, right, no leaf will flow, the leaf will not move in that channel for one specific condition.
Than the D.
If which?
If the B is lower than the D.
When will water not move from one to the other?
If it's equal.
If they're at equal what?
Level, high.
Equal heights. So water will not flow from B to D if B is at the same height as D. Water will flow from a higher gravitational potential field to a lower gravitational potential field. Give it a big fancy term. Basically, water will flow from a high place to a low place. So if that isn't moving, it's telling me water isn't flowing in there. And if it's not flowing in there, well then the height at B must be same as the height at G. And that's the analogy I'm using when I come back here. If my galvanometer isn't moving, it's telling me there's no current going up or down. And current will only move if there is a potential. So if there's no current, it must mean that the potential between those two are the same, just like the height between these two are the same. So therefore, if the potential between those two are the same, and that's got the same common point, well then the potential difference between AB must be equal to the potential difference between AD. Just like saying, let's come back here and make this analogy. If the water is flowing in this direction, right, and it's coming down here, and it's got a common height up here, let's say that's 100 meters high, and here it's, I'm making up numbers, that's 75 meters, and that's 75 meters. If I know that the water can go in two different directions, it can go that way, or it can go that way. Right, you're looking down, so you're looking down it like it's on flat, it's like you're on a helicopter. It can go there where it becomes a raging torrent, or there's a small little stream, it can come down here. But at this position, they're both at the same heights. They come from a common height here. So what can I say about the height difference there and the height difference there?
The same.
They must be the same.
But how is I1 the same from B to C? Because you've got a different resistance.
How is it the
Or
same
two.
there as it is there?
Yeah.
Let's go back to doing, so we get rid of this for now, and take another little aside.
Yeah.
If you've got a normal circuit, there's my normal circuit. There's one resistor, there's another resistor. That's 100 ohms, that's 10 ohms. Is it the same?
Oh
current
yes,
flow?
and the current. Yeah. Okay. Yeah.
So it's the same idea. Yep, same idea there. That's what it is there. Okay, so we take that. So that's just trying to explain all it, and in case anybody is confused, you don't have to remember all of this. It's just trying to reinforce some of the ideas we've come across.
Exactly.
Potential
Can I ask one
difference,
other
current
question?
difference. Just ask as many questions as you like.
Oh, no, just explain it. No, I get it now.
Okay? So what's the next step? And we do here. You remember, it's no big deal. You don't have, at this stage, it just becomes
Can you
mathematics. So
cross off the eyes?
well, let's we'll bring this guy
Put
down
that
here.
down
If
here.
I said I1 R2 there equals I2 R4. So I just taken that line and put it down there. By the way, next.
Oh, yeah, divide.
Divide. I'll divide I1 R1 by I2 R2. So if I'm dividing the left-hand side of that equation by I1 R2, and I want to keep an equals, I must divide the right-hand side of the equation by I1 R2. But instead of dividing by I1 R2, I'm going to divide by I2 R4, because it's equal to I1 R2, so it's the same thing. So basically I divide the left-hand side by I1 R2, and I divide the right-hand side by I2 R4. It's the same thing on both sides. And now these guys cancel, and I'm left with R1 over R2 equals R3 over R4, and it's right now that we kick back into memorizing mode. That equation you've got to use, and it'll only make sense if you can actually remember what way these resistors are arranged here. So if you rearrange these incorrectly, then this formula won't be used properly. You might be dividing when you should be multiplying and vice versa. Okay, so you've got to have R1, R2 on top, R3, R4 on the bottom. And you will be given an unknown resistor. You will be told one of those guys is unknown. Use the formula to find the right resistor. Anthony?
They just say we don't have to derive the formula.
Correct. You don't have to derive any of this, which you do have to know that bit up there.
But you should know a bit about it so that you can use one properly.
Yes, yeah. And also, like I said, the reason I went through it is just because it reinforces ideas what it is. It just gets you asking the questions one last time. So what we're now going to do, we said this is fairly impractical to find out the resistance of an unknown resistor. So what we're going to do instead is we're going to see how we can use that theory to come up with something that's much more practical to find an unknown resistance. Obviously you could just use an ohm meter to find an unknown resistance. This is another way of finding an unknown resistance, and there are also other applications of it. Okay, so far? I can rub off this, and we'll move along. Anthony, I'm still doing okay there, am I?
Yep.
There's time left, right. If I replaced all the bottom line with just a single length of wire, so I brought that down here, and I just used a single length of wire from there to there, and we use the same notation. This was A, B, what was this?
C.
C, D, yeah, that was it. Now, there is a certain resistance, let's call this A down as far as here, A, B, let's call my C down here. I should have used it straight across there, it doesn't make any difference. There is a resistance between A and D, yes? It's just so I just put in a length of wire. A wire, doesn't matter, I just want it to be uniform length. There is, and we'll call this R3, resistance associated with that wire. Resistance associated with
Why is it not?
R4. It's, remember when I had my two resistors, I chop and change all different types of resistors until one. And here you're just going to chop and change the length, over and back, along a resistor. You're increasing the reason. Keep doing that.
Oh, so it's because
Until this guy here no longer deflects. Sorry, Jan?
the galvanometer is because it's centered. Is that right?
This guy, yeah, this guy here
Yeah.
won't be in the center.
Okay.
That's right. Yeah, you can move it all the way over there.
But if it was in the center, it'd be.
And these two guys, if those two guys were equal, and these two guys were equal, and they were all the same, then it would be in the center.
Oh, okay.
But you're right, because these are all over the place, we don't know what those are. This guy here would be equal. So now, my formula as before, basically this is like a resistor. It's R1 over R2 equals R3 over R4. But now what we're going to say is we're not going to even look at those resistances. We're going to use, so we're not going to use that. We're going to say, well, R3, what can I say about the relationship between a resistance and length of a wire? As in, is the resistance equal to the sine of the length of the wire? Is it the length of the wire squared?
It's directly proportional.
It's directly proportional. And we looked at this when we did resistivity, and we're going to look at it again later on. So if I double the length of the wire, what will happen to the resistance? It will double the resistance. That's fairly straightforward, right? There's a certain resistance here. If I double the length of it, I'm going to double the resistance, right? So if I said R3 is proportional to the length AD, how can I get rid of my proportional sign?
Put in a constant.
It's equal to constant times the length, AD. Right, so that is what it implies there. Now we'll come down to here. R4. What's the relationship between R4 and the length DC?
Same. Proportional.
It's also proportional. Will it be the same proportional constant?
Oh yeah. You want-
Because?
Because it's directly proportional.
Yeah, and because it's the same wire. We're just moving along the wire. So it's the same proportional constant. So R4, equals K times DC. I should have said it's proportional to DC. Therefore, R4 is equal to K times DC. Okay, so far? This bit is important. Again, I don't think you'll have to remember it, but you will have to use the next line we're going to finish up with. So now, where I had R1 over R2 equals R3 over R4, I'm now going to say R1 over R2 equals, what do I say instead of R3? K times the length AD over R4, which is
KDC.
K times DC. What can I do to make that a little bit simpler?
Cross multiply.
Before I cross multiply? What's it, Connor? Cancel the case. It's the same case, the same proportional constant because it's the same wire. So now I've got R1 over R2 equals the length AD over the length DC. So now, rather than chopping and changing resistors, all I've got to have are two resistors up there. And let's say I don't know the resistance of one, but I do know the resistance of the other one. I just set them up like this, where I know the resistance of one of them, attach them to a long wire, and it's important that the wire is uniform and diameter because we're assuming it's the same proportional constant, so it's got to be a fairly well-designed wire. And all you do then is move the galvanometer connection over and back until such time as you get what?
No deflection.
No deflection, therefore there's no current, therefore the same derivation applies before as would apply now. When this happens, by the way, in case you are ever expressing it or talking about it, we use the phrase the bridge is balanced. When there's no current going through here, we say the bridge is balanced. So once again, you now have this formula. So all you need to find an unknown resistor, the value of an unknown resistor, is to have one other one where you do know the value and a length of wire. And you're going to break it up into a couple of bits and pieces. And we'd say there's more applications in this. This is a highfalutin way of just finding the resistance of the wire. But there is some applications of it which we'll see in a minute. So, while I'm talking about it, let's come back and demonstrate it.